Good morning and welcome to NASA headquarters in Washington. My name is Dwayne Brown with the Office of Communications. Ladies and gentlemen, the journey to Mars just got a whole lot more fascinating. This morning, scientists will provide further details on the answer to a long-held mystery of the red planet and provide their thoughts and theories on the possibilities of what this could mean for life beyond Earth. We'll have short briefings and presentations by participants. Then we'll open it up for questions starting here in Washington, our phone lines, and social media. The information you will hear today and any other updates are available online at www.nasa/Mars. Also, nasa.gov, Journey to Mars. And of course, follow the conversation, and the conversation is phenomenal all over the world of what is happening and what will be talked about today. Social media, YouTube, Twitter, Facebook, and send in your questions to #AskNASA. We've got a lot to cover, so let me introduce you to today's participants. First up, John Grunsfeld, 5-time space-flown astronaut and associate administrator or head of the NASA Science Mission Directorate here at NASA headquarters. Jim Green, Director of Planetary Science, NASA headquarters. Michael Meyer, Lead Scientist for the Mars Exploration Program, NASA headquarters. And ladies and gentlemen, joining us via phone from France, individuals attending the European Planetary Science Conference. Alfred McEwen, Principal Investigator for the High Resolution Imaging Science Experiment, or HiRISE, from the University of Arizona in Tucson. And Luigi Oja of the Georgia Institute of Technology in Atlanta. And joining us from the West Coast, from NASA's Ames Research Center, is Mary Beth Wilhelm. Hold on to your seats and your hats, and I'll turn it over to John.
Good morning, everyone, and thank you very much for coming. This is a very exciting discussion that we're going to have today. Science at NASA is all about innovating, exploring, discovering, and inspiring. And we have some very innovative instruments orbiting Mars, on the surface of Mars, state-of-the-art technology, and we're starting to put together a much more interesting picture of what Mars is like. I grew up during the era when Viking had landed on Mars and revealed a desert-like planet, apparently dead, and not as interesting as we see it really is. Our instruments today are showing us a much more dynamic and complex planet, and one that is exciting for a number of reasons which I'll describe. And when we explore, we make discoveries, and that's really the human element. Discovery is why we do science. We're trying to answer fundamental questions about our universe, about our home planet, about our solar system. Questions like, where did we come from? Where are we going? And are we alone? And usually when I say where are we going, I'm thinking in the cosmic sense. What's the future evolution of the universe? Or what's the future evolution of life here on planet Earth? But in this case, and one of the reasons I'm wearing my astronaut jacket, is because we are going to Mars. Our journey to Mars is a science-led expedition right now, but soon, I hope, we'll be sending humans to the red planet to explore, and science will lead the way. And today's announcement of a really fascinating result about current water on Mars is one of the reasons why I feel it's even more imperative that we send astrobiologists and planetary scientists to Mars to explore the question of, is there current life on Mars? It's one of the things that I find most fascinating and excites me about coming to work every day. The way that we do that is to use our analytical instruments. And so these are somewhat complex measurements. And it is because we're trying to observe from orbit or observe from one spot on Mars that this is so difficult. But the more we observe Mars, the more information we're getting that it really is a fascinating planet. From the Curiosity rover, we now know that Mars once was a planet very much like Earth, with warm, salty seas, with freshwater lakes, probably snow-capped peaks and clouds and a water cycle, just like we're studying here on Earth with our Earth science satellites, the water cycle here on Earth. But something has happened to Mars. It lost its water. But we still have, in the atmosphere and on the surface, for the most part, but we still have this question of, did life arise on Mars once? And can we find out? And we have lots of intriguing clues about that story. Still, that begs the question about if life started on Mars some 3.5 billion years ago, did any survive? Is there any life on Mars today? And that's a fascinating question, one that's going to take some time to answer, but technologically, we can answer. And we can answer it by sending rovers, and we can answer it by sending people. And I look forward to that day on our journey to Mars. The discovery we're going to talk about today really is most exciting because it suggests that it would be possible for there to be life today on Mars. And with that, I'm going to turn it over to Jim Green to describe a little more detail and background.
Thank you very much, John. You know, we're making enormous progress with our current orbiters and rovers, as John mentioned. And this is really to look at Mars because it is the planet that's most like the Earth. It is, of course, as we've talked about, the destination for human exploration going beyond Earth. If we go back perhaps 3 billion years and take a look at Mars, Mars was a very different planet. It had an extensive atmosphere. And in fact, it had what we believe was a huge ocean, perhaps as large as 2/3 of the northern hemisphere. And that ocean may have been as much as a mile deep. So Mars indeed 3 billion years ago had extensive water resources. But something happened. Mars suffered a major climate change and lost its surface water. Today, we're revolutionizing our understanding of this planet. Our rovers are finding that there's a lot more humidity in the air than we ever imagined. As we ingest the soils, they're moist, they're hydrated, full of water. These discoveries are very important, but they were only part of the hydrological cycle on Mars that we're just now beginning to understand. What we're going to announce today is that Mars is not the dry, arid planet that we thought of in the past. Today we're going to announce that under certain circumstances, liquid water has been found on Mars. Now, to give more of a background on those results, let me turn it over to Mike Meyer. Michael?
Thank you, Jim. For the first time, we have orbital evidence of the agent that has enabled water to flow on the surface of today's Mars. For years, we've had orbital spacecraft imaging valleys, streaks, gullies. All of them looked like water was an agent. It had something to do with forming them, but we didn't have any proof. And it was not until about 4 years ago that we found the active process on Mars today that showed that water was a likely culprit. These are called recurring slope lineae, RSL, for the rest of the press conference to save everybody the trouble of saying recurring slope lineae. These are dark streaks that form in late spring, grow through the summer, and then disappear by fall. However, for 4 years, the scientific community has been unable to explain the waxing and waning of these dark streaks on the surface. During this time, additional observations have helped us determine that a broader distribution of RSL than we expected. We're also finding that they are in expanded latitudes. These observations have narrowed the constraints for how RSL might form, but there have been no evidence for water until now. It is through the multiple spacecraft and the multiple years of observations that we've been able to make this discovery of water on today's Mars. And for further details, I'll turn it over to Dwayne, who will pass it on to our scientists.
Yes, let's pass it on to our scientists in France and at Ames, and let's see what this excitement is all about. You're here first from Alfred McEwen from France, attending the European Planetary Science Conference, and then Luigi Oja. Alfred.
Greetings from Nantes. So I'm going to provide some background on the RSL, and I have to explain why we have such a horrible acronym to deal with here. For us scientists, it's better to have a purely descriptive name. That way we can argue about how these formed and still use the same name. We don't want a name that assumes we understand what these are. So we're stuck with RSL. And so I'm going to give a little background, and then I'll turn it over to Luju to describe his new results. Could I have the first slide, please? So this first view is the title slide. It gives the title of the paper that's being released today in Nature Geoscience. And this is a perspective view as if we were on the ground. There's actually an orbital image, but we project it as if we're on the ground. And the black arrows there point to the tips of these RSL. They actually begin way up near the tops of this hill here. And they flow down over the bedrock, and when they flow out onto the fans at the bottom, that's where they stand out most distinctly. So these are the features we're talking about. And if I could go to the next view graph, this will show you a little animated GIF that shows you the time sequence of these features. So on the left is a black and white image. This is Palakir crater, and it's all along the north-facing and west-facing rim of this crater. You can see the black arrows point to many of these on the left. On the right is this animated GIF, and it shows the sequence where these start to form in the early summer. They grow either gradually, very gradually, or incrementally. Then they stop growing and they fade. Then they disappear. They're gone entirely for most of the Mars year. The following Mars summer, new features appear and grow that are very similar. So that's the full sequence of events that we've been observing with HiRISE over the last 4 years or so. And these features are very sensitive to the temperature. They form at different times, at different latitudes on Mars, all related to the seasonal variations at those locations. So they're very temperature dependent. And the darkening and the temperature dependence can be explained if these are seeps of water that seep through the shallow surface layer and darken the very surface layer. But we had no direct detection of water. That was just our best guess as to what these were. If you go to the next slide, this is a global map of Mars, and it shows where we have what we call fully confirmed RSL. As of a couple of years ago, this needs to be updated, but it's the same general pattern. There's 3 regions. One is the southern mid-latitudes. Another is Valles Marineris in particular, and there are a few other equatorial spots. And then in the northern hemisphere, we've seen quite a few of these now in Acidalia planitia. Luju is going to talk about his discoveries of hydrated salts in 3 locations that are marked on here. One is in Valles Marineris, in Coprades Chasm. Another is Palakir crater, which I showed you the animated GIF for. And then we see them in the central peaks of Hale crater and Horowitz crater. And John mentioned the Viking results. Well, Norman Horowitz was the principal investigator on the pyrolytic release experiment on the Viking landers, which was one of 4 experiments searching for life on Mars. They had a negative result, although there may be reasons for that. So then the last slide that I'm going to show you, if you go to the next one, this just shows Mars and its orbit around the Sun. And this is to explain a little bit about why we see these at different times in different places. So Mars is tilted on its axis about 25 degrees, very similar to Earth's tilt on its axis. So it has seasons like Earth when each pole is pointing towards the Sun. It's summer in that hemisphere, winter when it's pointing away. In addition, Mars has a more eccentric orbit, non-circular orbit than does Earth. So right now we have short and hot southern summers and cooler but longer northern summers. And so we see the RSL in southern summer in the southern hemisphere. We see them actually in northern spring in the northern hemisphere. And in the equator, we see them year-round, but they follow the sun. The slope is a particular slope is active in the season when that slope is getting the most sun, depending on how it's oriented. All right. With that, I will turn it over to Luju to explain the new results.
Thank you, Alfred. Good day, everyone. It is truly an honor to be addressing this crowd about our results and discovery. As Alfred mentioned, we have been investigating these narrow streaks on Mars ever since their discovery, mainly to elucidate their formation mechanism. We know from prior investigation that these features form on Mars when the temperature condition is ideal for liquid water to exist on the surface. However, as Alfred mentioned, a key evidence was missing until now, and that was their chemical identity. An excellent way to validate the hypothesis that liquid water plays a key role in the formation mechanism of these dark streaks is via spectroscopy. And this is what I will be talking about in this slide. So if you see in the slide, there's an orbiter shooting rays down, and that's basically what spectroscopy is. An excellent example to illustrate the theory behind spectroscopy is, for example, the reason why leaves look green. Our human eyes can recognize various colors. We can see red, blue, yellow, pink, etc. But the reason leaves look green to our human eyes is because a major component of the leaf, which is the chlorophyll, absorbs all the other lights our human eyes are sensitive to and reflect the green light. In the same way, we can view the surface of Mars in different color, which is what you see in this illustration, both in visible and infrared light, and see how light is absorbed by various minerals on the surface. We have an excellent instrument called CRISM on board Mars Reconnaissance Orbiter, which is what you see in this illustration, and it can observe the surface of Mars at various wavelengths. In this work, what we did was we went to these places where we see these narrow streaks and observed the interaction between light and the surface material to see if there was any spectroscopic evidence to support our liquid water hypothesis. So if we go to the next slide, in this slide, you're seeing an animated 3D fly-through of a peak with dark, narrow streaks flowing out of them. During the summer months, this peak can contain hundreds of narrow streaks. This is the same peak that Alfred was earlier talking about, Horowitz. We looked at the surface using the instrument I described before called CRISM to see if there was any evidence for the liquid water hypothesis. So if we go to the next slide, I can show you some of the results. Here you can see two squiggly black lines, which are our observation from the exact place where we saw the narrow streaks in the previous animation. These squiggly lines, they're called spectra, and you can observe few big dips in them. If you read the x-axis, you can see that there's a big dip around 1.9 microns, which means at that particular wavelength, light is being absorbed by whatever is present on the surface. Additionally, you see the same thing at about 2.14 micron, another deep, which means light is also being absorbed at this wavelength. And there are a few other smaller absorption features we see on the spectra. Now we can go here on Earth, we can go to our laboratory and find out which minerals can absorb light at these specific wavelengths. And I present that result in the colored squiggly lines, and I label it laboratory observations. We found that our observation on Mars is well matched by salts composed of chlorine and oxygen called perchlorates, and especially when they are hydrated. And that is really the key here, the hydration. The fact these salts are hydrated when we observe them means that there's presence of molecular water in their crystal structure. The spacecraft MRO that I was talking before observes the surface of Mars every day at roughly 3 p.m., which is the driest time of the day. So most of the liquid water would have been completely evaporated. However, the molecular water trapped inside the salt structure would be a bit more stable, and that is exactly what we observe here. This means that the source of hydration or the source of molecular water in the crystal structure of the salt itself is either due to these features called RSL or some other processes that created these streaks. Regardless, the presence of hydrated salts in these slopes means that these features are forming due to contemporary liquid water. We see similar spectroscopic signature in few other places around Mars. If we go to the next slide, this is Polytear crater. And you can see arrows pointing to some faded streaks flowing out of the crater wall. This is in a slightly different location in the southern hemisphere of Mars. At this location, actually, we have multiple observations from different times. However, we see the hydrated salts only when these streaks are biggest. At other times, when the streaks are narrow and short, we do not see any evidence of hydration. This, again, just like Horowitz, means that the source of hydration or the source of molecular water in the crystal structure of the salt is either due to the presence of RSL or some other processes that created RSL. Regardless, again, just like Horowitz, the presence of hydrated salts in the slope means that these features are forming due to contemporary liquid water. If we go to the next slide, the presence of perchlorate also has some other big implication for water on Mars. You can see the pure water stability on Earth. For example, if you take a glass of liquid water here on Earth, the water will remain in the liquid form until you hit 0 degrees Celsius, when it will start turning into ice. If the temperature approaches about 100 degrees Celsius, then that cup of liquid water will start boiling, and most of the water will start going into the vapor phase. Next, if we take the same glass of water to the surface of Mars, similar thing will happen. The water will freeze at 0 degrees Celsius, but because of the thin atmosphere of Mars, the water will start boiling as soon as the temperature reaches close to 10 degrees Celsius. Therefore, pure liquid water is highly unstable on the surface of Mars, and this is where perchlorate can help us. Next, consider a water mixed with perchlorate or perchlorate brine. If that happens, then the stability of that salty liquid water on the surface of Mars vastly increases. As you can see in the graphic, the perchlorate brine will remain in a liquid form until we hit negative 70 degrees Celsius, and will not start boiling until it is 24 degrees Celsius. Therefore, the presence of perchlorates vastly increases the stability of liquid water on the surface of Mars. Perchlorate also has one other huge implication for water on Mars, and for that, I'm going to turn it to Mary Beth to explain that.
And thank you, gentlemen. And we will now hear from Mary Beth Wilhelm. We'll go to the West Coast at the Ames Research Center. Mary Beth.
Thanks, Dwayne, and thanks, Luzu. So Luzu discussed the first major implication of our work, which pertains to the increased stability of liquid water on the surface of Mars. I will now discuss the second major implication and then discuss some of the broader significance of our findings. So perchlorate salts have a special capability pertaining to the absorption of atmospheric water through a process called deliquescence. Basically, if the humidity in the Martian atmosphere gets high enough, perchlorate salts will absorb the atmospheric water until the salt dissolves and forms a liquid solution. This is one possibility for explaining the formation of RSL. So this sort of physical process can explain the features that we observed here. The discrete darker patches observed in this image may be formed by deliquescence. It is also possible that the formation of RSL is due to other types of processes in which we won't go into depth on here. Perchlorates have a much higher ability to dissolve in water compared with other salts that we see at the Martian surface. So our observations could also be explained by some other liquid water source dissolving perchlorates that are naturally present in the soil and then later depositing them as a solid in higher concentrations. But again, deliquescence is our favorite scenario. So here you see a map of the distribution of perchlorates on Mars. The red triangles indicate places on the surface where perchlorates have previously been detected by rovers or landers. Perchlorate is suspected to be present at both of the Viking landing sites and was found in the northern plains by the Phoenix mission in the late 2000s. Most recently, it was detected at Gale Crater by the Sample Analysis at Mars instrument aboard the Curiosity rover. Our detection of perchlorates at RSL sites are shown here in blue, are the first to be made using data acquired by an orbiter. We have increased the number of known locations of this important resource on the Martian surface, showing that perchlorates are perhaps more widely distributed than previously thought. So to summarize, our findings strongly suggest that these recurring slope lineae are formed by liquid water on present-day Mars. The spectroscopic detection of hydrated perchlorates indicates that this water is briny and not pure. So with that, I'll now discuss some of the broader significance of our findings. So water, as I'm sure many of you have heard us say on multiple occasions, is an essential ingredient for life. Our results may point to more habitable conditions on the near surface of Mars than previously thought. Here, potential habitability by Earth-like microbes is unclear. To assess habitability, we would first need to determine how cold and how concentrated the brine is. But the detection that we've described warrants further astrobiological characterization and exploration of these unique regions on Mars. Finally, water may be an important resource for future human explorers and inhabitants of Mars, and may decrease the cost and increase the resilience of human activity on the red planet. Looking forward, it is imperative for us to further understand the source of these water for these features, as well as the amount. And with that, I'll turn it back over to you, Dwayne, at NASA headquarters.
Thank you, Mary Beth. Okay, ladies and gentlemen, we now will transition to our question and answer. We have a lot of media, not only here in Washington, but on the phone lines, and we want to get to social media. So I'm going to ask you wait for the mic. Please limit your question to one. We'll try to get to as many questions. Our participants will be here following the press conference, but we have a gentleman here. If we can get a mic here. And your name and affiliation, please.
I'm Chip Reed with CBS News, and I'd like to try to pin you down. Given all this new evidence, how likely do you think it is, a 1 to 10 point scale or whatever you choose, that today there is some form of life on Mars?
Okay, I guess everybody's looking at me, so I'll give you my feeling. You know, when you look at Earth, water is an essential ingredient, and just about, well, not just about, everywhere we go where there's liquid water, whether it's deep in the Earth or in the arid regions, we find life. This is tremendously exciting. We haven't been able to answer the question, does life exist beyond Earth? But following the water is a critical element of that. We now have, I think, great opportunities to be in the right locations on Mars to thoroughly investigate that. And I think the reoccurring slope lineae with the actual water on the surface allows us, with surface mobility that we have in our assets now and in the future, to be able to go over to thoroughly investigate that and indeed look for life and then make that positive identification.
And, go ahead, John. Yeah. I'm sorry.
Yeah, I just think the really exciting thing about this is that our view of Mars, of this ancient Mars, and the possibility of life originating on Mars has been really about seeking chemical fossils of possible past life on Mars. The existence of liquid water, even if it's super salty, briny water, gives the possibility that if there's life on Mars, that we have a way to describe how it might survive. And that we are now at a point, technologically, with over 50 years of successful space flight, that we have the capability to go there, ask this question of is there life on Mars, and answer it. This is, to me, the most exciting thing, is now that question is not an abstract scientific question. It's a concrete one that we can answer.
Michael?
Yeah, I would just like to add sort of a sensibility about how much we don't know. We have only one example of life, and that's us. This is it, on planet Earth. We don't know how it started. And so one of the things that we found at Mars is we know that Mars could have supported life, at least what we know about life. But we don't know how life started here, so we don't know if it's possible for life to have started on Mars. And so that's a huge question that needs further exploration. And it's only through that exploration that we're going to narrow the possibilities down and maybe get actually a direct answer.
Does that question, Jim,
I was just going to just expand a little bit on that. Now that we know what we're looking for, with HiRISE, we can begin a better search. We can begin to be more methodical. We can look and see if we can determine if there is some sort of aquifer network that may be supplying these. We don't know that. There are other theories, other ideas, but that is actually the next step. How much water that when it left the planet went into the soil, went underground. and that, as we said, is also a resource for human exploration for us. So if there is indeed those kind of resources that we can begin to probe, we might be able to answer that question pretty quickly.
So that question probably knocks out half of the questions we're going to get today. Let me see if our scientists in France or Mary Beth, if you all want to chime in on that question. We'll start with France. Alfred Aluji?
Well, I would just say that I think the possibility of life in the interior of Mars has always been very high. There's certainly water somewhere in the crust of Mars. And Mars has received meteorites from Earth. It's been contaminated by Earth, rocks, and we know that microbes can survive that trip. So it's very likely, I think, that there's life somewhere in the crust of Mars, microbes. But it's where is it, how accessible is it, is very difficult now. Maybe there's something we can find close to the surface, and that's what's exciting. But to me, the chances of there being life in the subsurface of Mars has always been very high.
Okay, just a reminder to our many social media folks, send in your questions at #AskNASA, and we're going to continue here at headquarters before we go to the phone lines, and we have we go this lady here, then here. Give your name and affiliation, please.
Hi, Anna Wilding, Herald de Paris newspaper. We publish in English and French. How will today's announcements affect your time frame for going to NASA and the possibility of coming back? And is any budget allocated towards cultural resources, finding any sign of cultural resources on NASA? I know you're looking at the water, but what about potential habitats or anything like that as well? Is there a budget?
Well, we do have a Mars budget for future scientific exploration, and in fact, we have a number of exciting missions that are queued up, both NASA-led and also European Space Agency-led with the partnership with Russia. And so we have the InSight lander, which is going to launch next year, and will tell us about the interior of Mars. It's the first time we're going to look into Mars by putting a seismometer, sort of an earthquake sensor, and a heat flow experiment to tell us about the interior of Mars. And so that's very exciting and is linked to these broader questions. The European Space Agency with Russia is launching a mission called ExoMars, also in 2016. And in 2018, they have a lander going down. And in partnership with NASA, we have an organic molecular analyzer. And they're going to have a deep drill that's going to drill under the surface, bring up materials, and analyze it to see if there's organic matter. Organic meaning related to carbon compounds, but specifically ones that might have been created by life. So that's very exciting. And then in 2020 is our next big NASA rover following on Curiosity that will actually collect samples so that eventually we can bring them back to Earth, put them in our best analytical instruments, and see if we see any signs of ancient or conditions that would tell us that there's life on Mars. That's just the beginning. That's just in the next 5 years. Beyond that, we have lots of plans as part of our journey to Mars that include developing the Space Launch System, a big rocket that will better in the future be able to get payloads to Mars and perhaps a round-trip mission. And we're still sketching out what that looks like. The future is always more fuzzy than the current, but certainly these exciting results only encourage us for the future of Mars exploration.
We also shouldn't discount what we currently have as assets that are there. They're actually relatively healthy. The Mars Reconnaissance Orbiter is doing a fabulous job. It's got high-resolution imaging, and as we talked about, the mineralogy and from CRISM that it's been doing. When you look at, even though it's been there nearly 9 years, it's only really mapped about 3 or 4% in high resolution of Mars. There's so much more that we need to do to really look and understand this kind of network all over the place. And with that, it'll enable us then to narrow down on some better places or more accessible places where we can get access to these kind of regions to really thoroughly examine. Curiosity is also in a nice location. It's in Mount Sharp. It's doing great. There's potentially some dark streaks that are on Mount Sharp. We don't know much about those. We don't know if they're reoccurring slope lineae. There's a possibility that more observations will eliminate those or give us more data that could tell us that they also could be RSLs that we might be able to visit. So there's some really exciting things just coming up, even with our current assets.
One more question, and then we go to the phone line. Sir?
David Curley from ABC News. John, let's talk about astronauts. This really is a breakthrough for human travel to Mars. You could now purify the water, create oxygen. This makes it much easier, doesn't it?
Well, I think all of the scientific discoveries that we're making on the surface of Mars, at Curiosity at Gale Crater, these observations from Mars Reconnaissance Orbiter are giving us a much better view that Mars has resources that are useful to future travelers. When you have water, what's water? Hydrogen and oxygen. That's what we make rocket fuel out of. Perchlorates. The space shuttle, the solid rocket boosters are aluminum perchlorate. In principle, you could make solid rocket fuel. And as we've talked about, perchlorates are ubiquitous around Mars. But the water really is crucial because we need water to drink, oxygen to breathe. We have carbon dioxide, also oxygen. So there are plenty of resources on Mars, even nitrogen in the atmosphere, which we don't usually think about because for us it's relatively inert. But it's crucial for life, both if life exists on Mars, but also, once we get there, we're going to need nitrogen for a variety of purposes. So I think, Mars is looking more and more that, it's a potential habitat for extant life on Mars that could be, as you heard, from transfer from Earth one way or the other. Some people say we're Martians. It could go either way. But the exciting thing is that I think we will send humans in the near future to Mars. There'll be scientists looking for signs of life. And also to be able to live on the surface, and the resources are there.
I think it's important to realize that NASA's approach to exploration is not Star Trek. It's not go where no man has gone before, as they say. It's really a very methodical approach for which we learn everything about the environment that we're going to subject humans to that we possibly can. And that's why our rigorous scientific program is really the pioneers that are making steady discoveries. And I anticipate continuing to do that for many, many years before humans even get into the vicinity of Mars. We'll make rapid progress in these areas. That does indeed help us understand the parameters and design better missions, leverage and utilize the resources that are available, and even make those kind of trips more feasible in the future than ever before.
In fact, I'll be very specific. On our Mars 2020 lander, we have an experiment that's not a classical science experiment. In fact, it's a in situ resource utilization experiment. So you may hear that. We love our acronyms, ISRU. But it's a small apparatus that's going to take in Martian atmosphere, mostly carbon dioxide, and extract the oxygen. And that's its function. We know we can do that on Earth, but we're going to demonstrate it on Mars. And that's part of our combination of human space flight, space technology, and science all in one.
Now, in addition to that, on 2020, is underneath the rover is a radar. Actually, it's from Norway. They're building it, the Norwegian Space Agency. And this is a radar that will send radio waves through the ground, return reflections, will tell us what that strata is like. And it might be able to uncover aquifers that are close to the surface. It could tell us how important experiments like that are for humans to be able to take and go to Mars. And in fact, the MOXIE instrument, which is great, we're going to operate that all times during the day. There's huge temperature and pressure swings on Mars. So what is it like? What's the efficiency of extracting the oxygen under various extremes, not only during the day, but all throughout a season? So these are huge steps for us to be able to plan the right resources to support humans in the future.
Okay, let's go to the phone lines now. And we're going to start out with Ken Chang of New York Times. Ken?
Hi, thanks for taking my question. So you always say how exciting this is, and you wanted to go study the possibility of current life. I was wondering, when would you actually get there, since none of the current spacecraft there or being planned have been clean enough to go to a special region. I heard Dr. Green say that Curiosity might go to these dark streaks. Under what parameters would that happen?
Ken, you brought up a really important point, and I know Michael and Jim will comment on this. But the question of, is there life on Mars? We know there's life on Mars already because we sent it there. We try and clean our spacecraft as best as we can. And the Vikings certainly were sterilized the best of any of our spacecraft because we just didn't know. But the surface of Mars is really a very harsh place. It's got ultraviolet light from the sun that bakes the outside of the spacecraft. And if you want to kill microbes on Earth, you take a UV light. and you kill the microbes. We've cleaned the spacecraft as best as we can, but we know that microbial life, bacteria, are so tenacious that it's impossible to kill them all. So we do the best job we can, and then we send our spacecraft into areas that we think are the least sensitive to the possibility of contaminating extant Mars life. And so what Ken Chang of the New York Times has suggested is, how can we take a spacecraft like Curiosity that may not have been cleaned as well as, say, Viking, to an area that might have extant life? And it's a great question. But this is the scientific process. This is why we're crawling before we walk, so to speak, that we're being very careful that we don't send a spacecraft to Mars with the intention of detecting Martian life and find out that we detected the Earth life we took with us. And this is the general, that's tough to do. Yeah. When you actually go down and list, how do you avoid doing that? It's very hard. And this is the general field that you may hear us talk about of planetary protection. It's not only protecting the Earth from bringing some alien life form to Earth, but more so right now, it's protecting the environments that we go to, whether it's Mars or Europa, to make sure that we don't contaminate other planets before we find out if we're alone in the universe.
Yeah, we don't really know if Curiosity will have an opportunity to be able to go to one of these areas and find, make measurements. We, as I mentioned, have some linear streaks on Mount Sharp that we just don't know enough about. They may or may not be RSLs. We've got a lot of work to do on that. And then we have to make decisions on, is Curiosity really good enough to be able to go over to that area and make appropriate measurements with as John said, without it measuring us, without it measuring things that we might have taken with us. But even then, it has a limited set of capability to be able to make any sort of detection in this area.
Next up, Tim Risen, U.S. News and World Report. Tim?
Yes, thank you. This is Tom Risen with U.S. News and World Report. Yes, congratulations, everyone. Great research on Mars. Very exciting to hear that the surface of Mars can, at some point, support water. It sounds a bit like Game of Thrones, where there's extreme seasons where it gets really cold, then it gets really warm. Do you think that if we hit it right on one of the warm seasons, that humans could grow crops on Mars, that the soil would be alive enough to support some kind of Earth crops?
Well, I think the real challenge, and if you think about the progression of altitude on Earth, as you climb a mountain, say you're climbing Mount Everest, when you're in the verdant valleys of Nepal, you have wonderful plant life. But as you go higher, that plant life sort of disappears till you see only lichens on rock, which are this unique symbiosis between fungus and algae. And as you go a little bit higher, all the plant life disappears. That's largely because the atmosphere gets so thin that any life would be desiccated, would lose its moisture. Well, Mars is the altitude is an Everest that's 3 times higher than any airplanes can fly. And so you'd have a challenge growing plants on the surface of Mars, even with maybe some extreme genetic engineering. But certainly you could build inflatable or small greenhouses with higher pressure. And if there's a lot of water on Mars, you could then use that water to grow plants inside the greenhouse. Because after all, it has plenty of carbon dioxide, which is what plants breathe to create oxygen. So that might be another mechanism that we have future explorers with the plants that they eat as part of the system to provide environmental conditions.
And now we know there's a significant amount of water and the humidity and water resources to be able to bring to bear.
Hey, next up, Reuters. Irene.
Thanks very much, Dwayne. I also had a question about planetary protection issues. I understand Mars 2020 doesn't have the budget to do a necessary sterilization to go to an area of special interest, and just was wondering, in light of this discovery, might that be revisited, and could the landing team consider sites close to RSL locations?
Budget question.
Well, indeed, the current sites that are being considered for Mars 2020 are being classified relative to planetary protection. And our plans indeed are to make sure that Mars 2020 does indeed recognize what classification and then sterilize appropriately at a particular level. Returning samples is one of the highest levels of planetary protection no matter what. And so we have a whole variety of plans to be able to sterilize Mars 2020, and we have the budget in the plan to be able to do that. So it's incorrect to say we're not going to consider planetary protection on 2020. We are, and we have plans in terms of how to handle that.
I think the other part of that question, though, is that these RSLs, these streaks of briny water, are in challenging locations. So to design a rover, and the 2020 rover is the same design as the Curiosity rover. Curiosity has gone up some pretty steep slopes, but some of these briny features are on very steep slopes in tough terrain that would be trivial for an astronaut in a spacesuit to go up and investigate, but very hard for a rover. So we're a little ways off. So I think that the investigation of these with proper planetary protection lays in the domain of future robotic spacecraft that are designed specifically to go there and that are designed in a way that they can be appropriately sterilized. And I think the exciting thing about this announcement is it's the confirmation of what we suspected, that this is due to some kind of water feature that I think will really drive the ingenuity of our engineers and scientists to come up with a viable experiment, and hopefully that we can do in the 2020s, that would go and investigate these areas and perhaps even return samples from these areas someday.
Okay, Irene, we're going to get your planetary protection question another time. We'll have to do a lot of follow-ups. I believe folks in France want to respond to the question, and please identify yourself.
Hi, this is Alfred. I was going to say exactly what John just said, that these RSL are on steep slope. That's the RSL that we know about. There may be water from deliquescence on flat areas as well that we just don't know about. And the problem is that we observe with MRO at 3 p.m., the driest time of day. So with a morning orbiter, maybe we would see, and high-resolution observations, maybe we could find this in other locations that are more accessible. But right now, these are only known to exist on these very steep, rocky slopes, places we can't land directly. We could land close to them and observe them from a distance, so it'd be remote sensing from the ground, and that would be valuable, especially to watch these things throughout the day, which we can't do from orbit.
Okay.
I would also just say that if I were a microbe on Mars, I would probably not live near one of these RSLs. I would want to live probably further north or south, higher latitudes, under the surface, quite far under the surface, and where there's more of a freshwater glacier. We only suspect those places exist, and we have some scientific evidence that they do. And that's the subject of future exploration, when we can find subsurface ice that's a few meters or deeper below the surface, and that's freshwater. And I think that's going to be a very exciting area of exploration in the future.
All right, we're running short on time, but we're going to take one more call from the phone, social media, and then come back here. Keith Cowing on the phone.
Question for Michael. Hear me?
Yes.
Can you hear me?
Yes, I can.
A question for Michael Meyer. This is sort of the perennial question I have, that you guys always say you want to look for life on Mars, but you don't know what Mars life looks like, and since you don't know what it looks like, you don't know how to look for it. That said, this discovery is just a series of papers that have finally come to a conclusion about the water and the perchlorates. A, are there analogs on Earth that you are very specifically looking at that mirror aspects of what you found on Mars? And B, as you prepare to send people there and maybe more robots, have you ever given thought to building a large refrigerator and trying to simulate the geology by dumping stuff in there and seeing how it reacts and then inoculating it with known life forms?
So, number one, we are actually looking for life on Mars. We're taking a very measured approach to it because in many ways we don't know what exactly to look for. So we're looking for things that frame it and give us a context to make us understand whether or not life was even possible, and then what may be sort of a biochemical discontinuity that would be a clue that life was there. And included in that search is, in fact, the idea that we're going to cache samples in 2020. This has been a long-standing scientific opinion from the Natural Research Council, et cetera, is that the only way we'll ever be able to tell whether or not there's life on Mars is, in fact, to be able to bring a sample back to look at it thoroughly to understand what is there and what the possibilities are. Yes, there are some Earth analogs, and then, in fact, they see streaks forming that look similar in places like Antarctica. The difficulty is that something that looks the same doesn't mean it is the same, so we don't know if it's the same mechanism, but at least we have something that visually looks similar, and that's being studied. The idea of throwing stuff in the freezer and seeing if it grows, I think the food industry does that all the time. And that's one of the things that helps set what the temperature of your freezer is, which is around -20, because you don't get things growing in them.
I think the other point to make is that the scientific process and how we decide what missions to send that are our large strategic missions, like Mars Science Laboratory Curiosity, like Mars 2020, is based on a rather large scientific community that's heavily influenced by scientific discovery. That's the scientific process. And in just about 5 years, we're going to start up the next major review of planetary science. And I can anticipate that with the results from sample analysis at Mars, the SAM instrument that shows perchlorates at Gale Crater, that shows organic materials that had a transient methane signal that we still don't know what it's from these results on RSLs and all the rest, I can't imagine that it won't be a high priority for the scientific community to send something that has the right planetary protection to go to these areas and may have a life detection capability to see if there's life there that's similar to Earth. And that may, that's always risky, because what if you don't see it? That doesn't rule out life. It just means it's not just like us. And from an evolution standpoint, you wouldn't expect that. So let me close this out.
Oh, no, we still have to. Yeah, not yet.
Okay.
We got a few more minutes, but then we'll let you close it out. Let's go to social media. Emily, I know we've got a lot of questions, but let's take 2 quick ones, and then I'm going to give Associated Press on the phone, Marcia Dunn, 1 question, then we come back, and then I'll turn it over to the boss. Emily, what we got?
Sure. Yeah. This first question is from Melissa on Twitter, and she said, so you found water. What are the next steps? What do you plan to do with this information?
Drink it.
Drink it.
Well,
yeah, let's do that.
I mean, one of the big things is, okay, now we found water. We see it participate in forming these streaks, but we don't know where the water actually comes from. And so it could be hiding a major source of water in the subsurface, but we don't have any idea. And so this is sort of the next puzzle to this recent discovery.
And a critical part of that is to find out other places on Mars that we see this. As Jim said, Jim Green said, we've only imaged about 3 to 4% total at this high resolution and different times a year. So
yeah, we need that high resolution. I mean, these streaks are maybe 4 or 5 meters in width. They may be a couple football fields long, but with our normal imagers that measure a half a kilometer by half a kilometer, they're totally lost. We need that high resolution imaging. We need that ability to see this table in several pixels from orbit, and we have that with HiRISE right now.
Hey, 1 more question.
Sure. This one's from Meredith. She said, does this mean that it rains on Mars? Is there a full water cycle like there is on Earth?
So we haven't seen rain on Mars because the surface pressure is way too low, but we have seen snow. And so even today, we know from the humidity, the fact that when the sun goes down, it cools, the humidity precipitates out as ice crystals on the surface of rovers and on rocks. So we know there is a water cycle. And we know from the evidence of Curiosity roving on the surface that 3.5, 4 billion years ago, there was a very active water cycle because we're driving over river deltas. And so at that time, it certainly did rain.
In fact, the Phoenix lander, which landed very close to the North Pole up in what we'd call the Arctic Zone region of Mars, actually made some great observations with their LIDAR, and that was a Canadian instrument from the Canadian Space Agency, watching the snow come in. I mean, there's some really great data from Phoenix alone that shows us that.
Before we go to the phone, one last time for social media, keep sending those questions in at #AskNASA. We'll have folks responding as quickly as possible to all of your questions on social media. So, on the phone, Marcia Dunn, Associated Press. Marcia.
Yes, can you hear me?
Loud and clear.
Yes, my question about the RSLs, would you anticipate the water being as salty as the Earth's oceans? I'm just wondering on the salinity. And can you even estimate or guess how much water we're talking about flowing? I don't know if I'm envisioning streams, rivers, a trickle. Is there a drought? Just sort of give me a picture of what you think, how much water there might be and how salty. Thank you.
Could I attempt that one?
Yeah, Luigi, did you copy that question?
Yeah, so Alfred's going to answer that question.
Okay, go ahead, Franz.
I'll say what I think, and Luigi can chime in as well. But Earth's oceans seem pretty salty to us, but water can get much, much saltier than that. And if the process of deliquescence occurs, if that's how the water is being made, it will be much, much saltier than Earth's oceans. How much water? We made an attempt to estimate in part of Alice Marineris how much water might be the minimum amount to explain the darkening, assuming only 5% water, which is sufficient photometrically to darken it, and only 10 millimeters thickness, which is enough for it to actually flow down the slopes. The minimum was 10 to the 5th cubic meters of water, which sounds like a lot if it was all in one place. I don't know how many Olympic swimming pools that is, but that's dispersed over very wide areas. And so what we're dealing with is wet soil, thin layers of wet soil, not standing water. But Mars does a lot of surface area, so if you could add it all up, it could be a significant volume.
Okay. All right. What I'd like to do now is turn it over to Dr. John Grunsfeld. And obviously, Mars, the Mars missions and Mars program is in his portfolio, but he also has nearly 100 missions in the science portfolio. So, sir, wrap up.
Thanks. Well, again, thank you all for coming. I know this is an exciting and interesting result. I know you'll have lots more questions. We'll try and answer the questions from social media. We encourage you to talk to our scientists after this. We are on a journey to Mars, and science is leading the way. And I think each time we learn about something new about Mars, Mars becomes more and more interesting. And I think it's just going to provide us with a great sense of our place in the universe and our solar system in particular. As Dwayne says, we have a lot of other missions. We've just started this year a mission to Europa, which we know has an undersea ocean, and we'll be exploring that in the next decade. So please stay tuned to science because basically science never sleeps. We have lots of discoveries, and we appreciate your interest. Thank you very much.
So with that, thanks for joining us from Washington, D.C. Again, go to nasa.gov/Mars, nasa.gov/Journey to Mars. Follow us on social media. Ladies and gentlemen, NASA's journey to Mars is very real. Thank you.